It's been a while since I wanted to make a video explaining the reasoning behind my particle animation, showing a charged particle's trajectory in an electrostatic field. Today, I finally have the time to share how I got to be able to create said animation. There are some important things I should be saying before diving in. To begin, I'll assume you're at least comfortable with the concept of vector fields and some numerical approximation methods. These concepts will be important for this video, but I won't be covering them in detail. I'll walk you through some basic ideas I had in the mathematical construction of the animation. Quick disclaimer, my construction might not be super accurate, as one would need to consider already known physical phenomena, like Maxwell's equations. The math you're about to see comes naturally from very basic and almost trivial observations, and therefore it lacks formality. This video should only be taken as an example of how one can begin to model a physical phenomenon using math. That being said, let's begin. Let us consider a two-dimensional plane in which there is, for the time being, one charged static particle and an additional moving one. If we were asked to draw arrows, which in this case will represent vectors, showing how we think the static particle affects the trajectory of the moving particle, we all may have different ideas in mind, but for me, the most natural drawing would be vectors pointing inwards to the center of the static particle, assuming opposite charges, of course. One can argue as well that those vectors grow in quote-unquote strength the closer they are to the particle. In this drawing, red vectors carry bigger strength. We have to understand exactly what this drawing actually represents. In order to do so, we can picture our moving particle with a starting velocity vector and imagine its behavior as time goes by. I hope this helps visualize that all the vectors pointing into the static particle, which we initially drew as a mere abstraction of the moving particle's behavior, actually represent the change in velocity of the particle, or in other words, its acceleration. Let's also remember that the acceleration is the second derivative of the position with respect to time. In light of these observations, we can safely deduce a differential equation describing the particle's movement. Of course, we are yet to define the vector field f of xy that describes the particle's acceleration. We need to devise a function that maps each point on the plane to its corresponding vector in our drawing. Two key observations will help us define this function. Number one, the closer a vector is to the static charge, the stronger the force experienced by the moving charge. And number two, all vectors point directly towards the static charge. The first observation can be expressed mathematically by visualizing the graph of the static particle's attraction force. Let P1, Q1 be the position vector of the static charge. We'd expect said graph to reach a maximum value exactly at P1, Q1, while at the same time becoming lesser the farther we get. I hope everyone agrees that this graph closely resembles the behavior we just described. Numerous functions could potentially look like this. For simplicity, let's define the magnitude as closely to what I consider to be the quintessential function for this particular case, a two-dimensional Gaussian function. The magnitude will then be defined as some constant c times e exponentiated to negative x minus p1 squared plus y minus q1 squared. Different values of c will yield higher or lower maxima values, resulting in a stronger or weaker attraction force. For observation 2, we need to find a function which we'll call h of xy, such that any point on the plane xy points directly towards p1, q1. It is considerably easier to find such a function. We'll only need to define h of xy equal to the vector p1 minus x, q1 minus y. One small problem, however, is that this h function will tamper with the vector's magnitudes. You can see for yourselves that the farther away xy is from p1, q1, the bigger the magnitude of p1 minus x, q1 minus y. This will undesirably interfere with our already defined magnitude function. The simplest solution here is to normalize the h function, ensuring that all vectors have a magnitude of 1. This can be done by dividing over the original magnitude of the vector. In other words, let's define h of xy as p1 minus x, q1 minus y, divided by the Euclidean norm of p1 minus x, q1 minus y. Combining our conclusions for both observations, we can finally define the vector field f of xy equal to the g function times the h function. After substituting, our differential equation now looks like this. Everything up until this point has been purely mathematical reasoning. However, with our already defined set of differential equations, we are in shape to translate into something we can compute. We could use any numerical method to approximate the solutions for xt and yt. However, in order to not complicate things too much, let's recall the definition of the derivative. We know the derivative of some function f at some point t equals the limit as h tends to 0 of the difference between f of t plus h and f of t over h. Naturally, this means that for small values of h, say h equal to 0.01, this expression is almost equal to the derivative of f at t. Let us remember as well that the velocity is the derivative of the position, and the acceleration is the derivative of the velocity, which yields the following approximations. Here, Vx and Vy represent the velocities of the x and y coordinates respectively. Likewise, Ax and Ay represent the accelerations of the x and y coordinates. By assigning arbitrary initial values for xt0 and vxt0 and rearranging some terms, we can approximate the velocity of the x-coordinate at t plus h. The same process is applied to approximate the velocity of the y-coordinate, as well as the position coordinates xt0 plus h and yt0 plus h. From this point, it becomes a matter of iteratively recalculating the position xy and velocity vx vy for each step. By implementing these calculations in your preferred programming language, you can simulate the motion of a particle within an electrostatic field created by a single static charge particle. The generalization for more than one static particle is very simple from here, however, I won't be able to cover it in this video. Additionally, in my original animation, I added a variable related to the loss of velocity due to air resistance, which makes the particle halt after a while. If you'd like to see these implemented mathematically, feel free to let me know in the comments. I hope this explanation was clear enough to serve as a starting point for any ambitious mind out there to make a modeling project of their own. Without anything further, thank you all so much for watching.